So that one was kind of the same AS. You're going to get diols. If you have mild oxidation, cold dilute alkaline KMnO4, if it's hot concentrated acetaldehyde KMnO4, the double bond would break down completely. And when it did, there were three scenarios. No carbon chain, it would produce carbon dioxide. The carbon had a single carbon chain, then it would turn into a carboxylic acid. If it had two carbon chains, it would turn into a ketone. And then you had, so we did some examples for that. We did the oxidation of alcohols. We talked about primary alcohols turning into aldehydes and then turning into carboxylic acid. Secondary alcohols were turning into ketones. And we did some examples for that as well. And we did the reduction, which was the reverse, that a carboxylic acid would turn back into an aldehyde, it would turn back into a primary alcohol. So we did that as well. And then we had oxidation of arenes. This was your A2, this is part of A2. Arenes, whenever you have a carbon chain, it simply gets oxidized to a carboxylic acid, no matter what the carbon chain is, whether they are two carbon chains or three carbon chains, or no matter what the number of carbon atoms are, the number, just a second. So no matter what the number of carbons are, just hold on one second. Can you guys hear me? Hello?
Yes, sir.
Hello.
Achha, so just 1 second. The board is hanging up. Let me just try and open the board again. You just wait 1 second. Not sure what's going on. Just wait 1 second. Maybe the website is down. Can you try and click the link on in the WhatsApp group and see if this is working? Let me just open a different board. Yes, I think it's up. So this one, just 1 second. So let's go. So it's back. Now this one, we did redox, and I talked about oxidation of arenes. I told you that no matter what the carbon chain is, no matter how big the carbon chain is or how small the carbon chain is, it just simply turns into these things. They simply turn into carboxylic acids. That's it. Just remove the carbon chain, put a carboxylic acid group in its place, and that's the oxidation of arenes. We did the reduction of different nitrogen compounds. Nitrobenzene, tin plus concentrated HCl, the NO2 turns into NH2, the hydrogens get added, that's reduction. That's how phenylamides are formed. Reduction of amides, you've got an amide, which is cetyl bond O and NH. You reduce it with LiLH4 and it turns into an amine. It's no longer, there's no longer an oxen over here. And in its place, you've got hydrogens. And then there was reduction of nitriles that was with LiLH4 as well. You've got a CN, hydrogens get added to it, and that turns into an amine. So that was pretty much all of it. This was all of the oxidation of, so this was pretty much it. So the next thing we're going to try and cover is the remaining reactions that we have kind of missed out on. So there are lots of reactions that are still left, not lots, but one very important reaction that you need to know is the formation of azidides. So we're going to do that. That's very important as well. So let's try and do the formation of dyestuff, which is azidides. So dyestuff, I mean, most of your paints, etc., are made from this. These are known as azidides. They're very stable. They're very stable dyes. So very stable. Now remember, paints have to be any paint, any sort of paint. It's got to be very stable. And the reason it's got to be very stable is that it has to withstand a lot of sunlight. It has to withstand. I mean, you're always washing your cars. There's a lot of dust falling on it. There's a lot of particles hitting it. So paints have to be really, really stable because they're exposed to a lot of the environment. Like you paint your house, it's a lot of things are falling on it. So they've got to be very stable. If a car has black paint on it, the black paint has to remain black for a very long time. It has to sort of be very, very stable. Now, what's an azo group? We'll discuss that later. The first thing is what would be your starting material for making an azo dye? Usually, the starting material is you start off with the phenylamine. So here's so you take a phenylamine. There might be other groups attached to it, but at the moment we're trying to make the simplest. We're trying to make the simplest azo dye. So you start off with this thing. It's N triple bond N. So it's NH2. That's phenylamine. So it's simply NH2, and that's your phenylamine. And what then happens is you react it with NaNO2 and HCl. Plus HCl. This is also sometimes referred to as HNO2 because NaNO2 and HCl, they react together to form HNO2. So it's sometimes referred to as HNO2. NaNO2 and HCl are the raw materials from which you make HNO2. So basically the reagent is HNO2, but usually you just add NaNO2 mixed with HCl. And the temperature has to be less than 10. So it has to be a very cold environment. So temperature has to be less than 10, and I'm going to explain why. But the first thing is, under these conditions, this thing turns into a diazonium ion or a diazonium salt. So this thing over here, from phenylamine, it's going to turn into a diazonium salt or a diazonium ion. A diazonium salt is a very unstable compound. It's basically N forming triple bonds with another nitrogen atom, and it's got a positive charge. That's what a diazonium ion is. And there would be, because the solution has HCl, so there might be some Cl ions around as well. So that is what a diazonium ion is. So this diazonium ion C6H5 and N2 plus 1 ion. That's the diazonium ion is extremely unstable. So it's very, very unstable. What happens is if the temperature goes above 10, it decomposes. This ion does not form. If the temperature is above 10, it's going to decompose. So you should not increase the temperature above 10. And you should know this temperature, if the temperature is greater than 10 degrees centigrade and there is water involved, this diazonium ion will decompose as it's going to decompose into a phenol. It will react with water. You need water for that, for decomposition as well. And the whole compound would decompose and it will form a phenol. The N triple bond N will break down, and NH4 plus 1 ions would also be produced. But that is if you, I mean, you're not supposed to take the temperature above 10. So it decomposes. We are more interested in this diazonium ion. This is something that we are interested in. Now, this diazonium ion is a very good electrophile because it's a positive ion. So C6H5, so this C6H5N2 plus 1 ion is a good electrophile. It's attracted to electrons because it's a positive ion. So it's a good electrophile, and it gets attracted to the benzene pi electron cloud. So it's attracted to the benzene pi electron cloud. So that's the first step. Step number 1, you make the diazonium ion. The temperature has to be less than 10 degrees centigrade. Once this ion is formed, make sure the temperature doesn't go above 10 because it will break down and decompose into a phenol, and it will react with water and form ammonium ions. So what do you do with this diazonium ion? This diazonium ion then goes and reacts with benzene. So this ion, I'm going to take this ion, forget the Cl-1, just this ion, and I'm going to make my dyestuff from this. So this thing over here will react with an activated benzene. So ignore this. This one will react with either an OH, it's got to be an OH, a phenol, or it will react with a phenylamide. So two things. So the second option is it's going to react with NH2. What happens is, and this has to be an activated benzene, the one that has high electron density in its pi electron cloud. Why does it have high electron density? Because the lone pairs on oxygen, they overlap with benzene's pi electron cloud, and when they overlap, the electron density increases at positions 2, 4, and 6. The other one must be an activated. This phenylamine, the same thing. The lone pairs on nitrogen, they overlap with benzene's pi electron cloud, and the electron density increases at positions 2, 4, and 6. So this N triple bond N plus 1 will be attracted to these positions. It's either going to be attracted to position number 4. It's a positive ion, so it will be attracted to the electrons at position number 4 or at position number 2. So it could be attracted to these positions as well. This other one would also, it's exactly the same. So you need an activated benzene, and the next step is an azo dye would be formed. What will happen is the product that's going to be formed in both cases is going to be this one. That you'll have, if I take the first one, what you'll have is the two things would join up. And let's make both of them. Remember, these two are separate reactions. So what will happen now is, I mean, this one had NH2. So both of them are activated. I'm going to remove the arrow, and this benzene would be bonded to this N, triple bond N plus 1. So they would form, so they're going to form a bond. The positive charge would vanish because it's going to get its electrons, and there's an N double bond N that's going to be left in the middle. The same thing happens to the first one as well. The electrons from benzene, they get attracted to the nitrogen in N triple bond N plus 1. The electrons, they get attracted, they end up bonding with it, and you're left with N double bond N in the middle. So that's basically your azo group. So it's, this other one has to be either a phenol or it's got to be a phenylamine that comes and bonds with the diazonium ion. And this is known as your azo group. This thing over here, that's known as your, so that's known as your azo group. Let me circle that. That's basically your azo group that's in the middle. And these are colored substances, and they're very stable substances. And every time, any paint stuff that you're trying to make, any dye stuff that you're trying to make, whether it's the dyes in your clothes or, I mean, dyes are used everywhere. Dyes are one of the most important chemicals in the chemical industry. People don't realize it, but everything has to be colored. And the color has to maintain its color. I mean, it's pretty hard for something to be very, very stable. Even if the clothes, if you have a red colored sweater, the sweater at all times must be red colored. Like after one washing with some chemical detergent, it should not change color. It should not react with it. So these dyes are extremely stable. They don't react with anything, and they kind of maintain their color for a very, very long time. You put them in sunlight, you wash them with different things, uh, different stuff falls on it, on your clothes. The paint does not change its color. And so that's about it. So that just took a couple of steps. The first one is, and this is something that this is one of their favorite. They give a lot of questions on this. So starting with phenylamine, you make a diazonium ion. What you do is you add NaNO2 plus HCl, and the temperature has got to be less than 10 because this ion is very unstable. It's acting as an electrophile because it's a positive ion. If by any chance the temperature increases by 10, it will decompose. So it's a very unstable ion. So as soon as this is formed, this unstable ion is reacted with an activated benzene. It gets attracted to the electrons, bonds with it, goes and bonds with it, ends up forming this azo group that's in the middle. So the activated benzene belongs to either a phenol or a phenylamine. The conditions that are required for this reaction are NaOH aqueous, and basically it's NaOH aqueous. And the temperature's got to be less than, it's got to be less than 10. So is this clear? You clear, Saruk? Is this clear? Munir, is this clear? Time?
Yes, thank you.
Zahir?
Yes, sir.
Acha, so that's pretty much it. So I'll just now the only difference between, like, what's the difference between a red colored dye and a blue colored dye? The only difference is this is the basic structure. Like you can have all sorts of stuff attached to it, all sorts of groups, other groups attached to it. So this is like the basic skeletal of every dye that exists, every azo dye that exists. You can have a CH3 bonded over here. You can have a CH2, CH3. So I'll just show you some azo dyes to give you an idea. Everything will have this basic structure. The only difference is between all the other stuff that's bonded to it. So a lot of times they use benzene as I mean, for example, this one. Maybe if we can, just a second. So probably remember these 3 double bonds, that's a benzene. So I'll just take a snapshot of this one. This is this is they're saying this is the orange color, that is orange 2. There are different names to these dyes. So that's orange 2. So if I just go and paste this over here, you'll notice that the basic structure is kind of the same. That the basic structure is kind of the same. It's the other way around, but the basic structure is kind of the same. If you look carefully, there's an N double bond N that's between two benzene structures. One of them is activated. One of them has an OH. The other one is not activated. The other one is not like a normal. I mean, that's a normal benzene, but one of them has to be activated. So the basic structure, like the one over here, that is present in this dye. Same is the case with this other azo dye that we saw, the red one. If you look at the red one, is there an azo group somewhere? Just a second. Yes, there is. I mean, and there are actually a couple of azo groups in this. You would have to look very, very carefully for this, but let me just. I mean, that's a lot more complicated structure, but you'll notice the main structure in this molecule. If we can. If you can put it here. So you'll be able to identify that there is an azo group over here. That's an N double bond N. One of the benzene is activated. It's got an OH. The other one is not activated. Is that clear?
Yes, sir.
What do you mean by saying it's not accurate, sir?
One of them is activated.
Okay.
I mean, one of them has to have either an OH or an NH2. Usually it's an OH or an NH2. Like that's the basic structure. You'll have benzenes connected together and there's an N double bond N in between. And one of them has to have either an OH or an NH2. So this one end up.
Okay.
Is that clear? So this red color dye has this azo group over here. That's an N double bond N. That's a benzene. And you got an OH over there. And the other one is not activated. So one of them has to be activated. Even over here, there's another azo group, which is over here, N double bond N. There's this benzene, that one is activated, this one is not. Right? Is that clear?
Yes, sir.
So you'll have all sorts of dyes, all these colored paints, etc. So even methyl orange is one such dye. Let me just show you images of other ones. So here's another one again. One of them has these N lone pairs which are mixing. This one is the activated one. There's an N double bond N. This is the other benzene. So two benzenes, one of them has to be activated. That's a tertiary amine because it's got a lone pair. There are no hydrogens, but there is a lone pair there. Which one is this? Is this an azo? No, not this one. We'll do a simpler one. So the basic idea hopefully is clear that this is. Anyways, this is another diagram. So you can have a look. So the basic idea is, let me just wait 1 second. So the basic idea is, this is your azo dye. This is the basic structure that would probably be present in every dye. Right? Is this clear?
Yes, thank you, sir.
Now, the difficult part is sometimes they will give you the azo dye and you would have to figure out the original reactants. Like over here, remember this. This is one thing that gets slightly tricky. Like if you look at it the other way around, what will happen is sometimes they'll give you the dye and you would have to figure out what the reactants are. Now, make sure when you break all you have to do is, when you have to think about it in reverse, You've got an azodie, you've got a azo group in the middle. Now, the original reactants would be, there would be one activated benzene. The activated benzene, the N triple bond N+1 will not be with the activated benzene. The N triple bond N+1 would be coming from the other benzene. Do you get my point? That if you have this starting point, and let me do this with an example. So let's assume we have this random azodie. Let's take this one. And I want to figure out the original reactants for this one, right? What two reactants made up this dye? So I'm going to split it up. I'm going to do the whole thing in reverse. Now, when I do the whole thing in reverse, what will happen is I need to decide where did the N triple bond N+1 came from. That's a big question. So remember, if I split this up, one of them was the activated benzene, the other one was not the activated benzene. So this thing over here, the N triple bond N+1 came from the other side. The activated benzene is the one. That would be one of my reactants. Right? So that's one reactant. And this azo group or the diazonium ion was the other one. So if I want to split it up, just make sure what the two reactants were. Like I'm doing the whole thing in reverse. So it was this thing. These were the two original reactants that ended up making this thing. That I had, one second, that I had, that's one of my reactants, that's the other reactant. This one would actually be N triple bond N, and it would be having a +1 charge. So is the idea clear that when you make an azodie, one of them has to be an activated benzene? The diazonium ion is not the one that's activated. The diazonium ion belongs to the other benzene. This is the same that we did over here as well. Like one of them is the activated benzene. The N triple bond N+1 was not with this benzene. The N triple bond N+1 was with the other benzene. If you want to find out the original reactants. So if you want to break up the molecule and find what the original reactants are, if you see an azo group, you would notice that one of them is the activated benzene. So the N triple bond N+1 must be coming from this benzene. Is the idea clear?
Sir, for NH2, sir, the benzene ring with NH2 would also be the activated benzene.
That's the activated benzene, okay? So it's either going to be OH or NH2 on the other side, okay? But the same over here. Like if I want to make this azodie, so if I want to break the azo group, where would the N triple bond N+1 belong? Would it be on that benzene, or would it be on this benzene? This one has OH, so that's the activated benzene. The N triple bond N+1 would probably be coming from this one. Is the idea clear?
Yes, sir.
So that's the tricky part. I mean, if you know the molecules, it's easy to make the product. You just have to put an N double bond in between, and you would join them up. But if you know the product, it's harder to actually figure out what the reactants are, because you would have to decide, where did this come from? Did it come from this benzene, or did it come from this benzene? So one of them is activated. It's going to belong to the other benzene. So let's do a couple of more examples similar to this. If I have other azodies, maybe this one. So that's a bigger image. So one second. I mean, your questions would be a lot simpler. These are slightly trickier. So this one, let's do this one. The original, what were the two reactants originally? Like if I want to split it up, N triple bond N+1, did it come from this benzene, or did it come from that benzene? Right side or left side? Which one is the activated one?
Left side.
Let me take this to the other side. Okay, if I have, यहाँ पे कर लेते हैं. Okay, if I have this thing, First thing, which one is the activated benzene? Remember, N has lone pairs. So which one is the activated one? It's this one, right?
Yeah.
So that means the original molecule, the N triple bond N plus one, the original reactants of this would be that the N triple bond N plus one would belong to this benzene. That would have been your reactant. That this thing over here would have been N triple bond N with a +1 charge. And this other benzene was your activated benzene that was going to react with it.
So yeah, how did you decide this?
I'm explaining that. Okay. Remember, go back to this reaction. There's a diazonium ion and it attacks an activated benzene, right? And what happens? Okay, in the middle, there's an N double bond N, which is an azo group. So what's happening is, okay, if you're given the original molecule, you have to decide where did the N triple bond N plus one come from? Was it part of this benzene or was it a part of this benzene? So remember, one of them is going to be your activated benzene. The N triple bond N plus one would come from the other benzene. Is the idea clear? Ibrar, is this clear?
Ji.
The answer decide, like you have to think of it in this way. So you've got two benzenes. One of them, if it has OH or NH2, it's an activated benzene. So that means the N triple bond N plus one did not come from this benzene, it came from the other benzene, right? So that is exactly what I did over here. I had an N double bond N in the middle. Okay, don't get confused. This is a benzene, right? This one was the activated benzene because it has an N next to it, and its lone pairs would mix up and the charge density would increase. So that means the N triple bond N plus one came from this other benzene. And the activated benzene was attracted, its electrons were attracted to the N triple bond N plus one. Is that clear?
Okay. Yes, sir.
Okay, is this clear to everyone? Sign clear? Ibrar?
Ji, sir, clear.
So let's do a couple of more examples because you would be asked to do this a lot. So let's take this example. Okay, I want to figure out so I want to figure out who my original reactants were. So this other example, I've got this molecule. So where did the N triple bond N plus one come from? This benzene or the right one? Which one is the activated benzene?
Right one.
Okay, so that's the activated one, right? So that means the N triple bond N plus one came from the other side. So it came from this side. So your original reactants were. Ignore the H. The original reactant were that this would have been your this thing over here would have been your N triple bond N plus one. And this other side would have been your, this other side would have been your, so this other side would have been, ignore the N. The N is not coming from that side. Is that clear? How to split this up and find the original reactants that make up this azo dye?
Yes, sir. Yes, sir.
Okay, so that's how you're going to do. Do this same as the situation with this one. This one, if you look at this one, the N triple bond N plus one would, this is the activated benzene, right? So the N triple bond N plus one would be coming from this side, right? Is that clear?
Yes, sir.
So that's the only tricky part that you have to remember, that where did the N triple bond N+1 come from when the azodie was being made? That's the only tricky part that's got to be remembered. So make sure that's how these two would join up. These two. So that's the only part. The otherwise, the whole reaction is kind of simple. It's simply you take you start off with a phenylamine, you turn it into a diazonium ion, and then that diazonium ion ends up attacking a phenol or a phenylamine. And the conditions are given. The temperature has to be kept at less than 10. Otherwise, the diazonium ion would decompose. It would turn into a phenol. That's about it. Okay, so let's try and do a couple of questions related to this. It's I mean, the questions are going to be. Let's do the simple ones first. Just a second. Just 1 second. Where's the questions? So this one is organic 188 nitrogen compounds. 1 second. So this one is mostly related to, that's more about proteins. We haven't done proteins yet. Not this, just a second. Let me. So no, not this one. This is not, no. That's one. So you're saying reaction number 4, first thing, the NH2 turns into, the first thing is the NH2 turns into the diazonium ion. It's N2+1, N triple bond N+1, and Cl -1. So what are the conditions? It's NaNO2 plus HCl, and the temperature's got to be less than 10 degrees centigrade. So temperature's got to be less than 10 degrees centigrade. That's one. And then he says that this dye is made. Now he's going to ask you, suggest the reagents for reaction number 5. What has been added? So remember, this is your activated benzene. So, I mean, this is your activated benzene. Right? So the N triple bond N+1 went up and joined with this benzene over here. That's your activated benzene. So that's your reagent, and any which aqueous alkaline conditions would be used. So this is the reagent that was added to this thing. Is that clear?
Yes, sir.
Yes, sir.
Okay, so the reagent added was this thing to this when reaction 5 happened, and the conditions were NaOH. They were basically alkaline conditions. There's another one. Now he's saying many of the food colorings. What is he saying? So now this one, although it's I said, but let's say if he had asked which one, where did the N triple bond N+1 come from? That side or this side? Like what were the
From the sunset yellow.
Okay, so the N triple bond N+1 is basically coming from this side, and that's your activated benzene. Anyways, he's asking what significance does this do? That he says that it contains sodium sulfonate groups attached to the rings. So there's a SO3 minus 1, Na plus 1 that's attached to it. Suggest, he says many dyestuffs used as food colorings, such as sunset yellow, contain sodium sulfonate groups attached to the rings. Suggest with an explanation a reason for this. So now this is completely random, but make a guess. Why do you need this group? What help would it do? I mean, it's a pretty random question, but I mean, you can make an intelligent guess. Like, it's a food coloring, and they're adding this group, so they're adding sodium ions to it. What do you think that would do? If can you even guess what difference would that make? SO3 minus Na plus 1.
Stability.
Like, what kind of properties should the dye have? It's a food coloring. Should it mix with water or not?
Dissolve in water.
Okay, so you want it to be dissolved in water. So sodium salts are very soluble. Plus, it makes the whole thing ionic. There's an ionic compound over here. Ionic compounds that dissolve. Like, if you have a group like SO3 minus 1 and Na plus 1, it will group 1 salts are soluble. I mean, if you remember, group 1 salts are all soluble. So these groups, water can come and get attracted to the negative ion over here. Is that clear?
Yes, sir.
So that was kind of random, but is there any other questions similar to this? I mean, there are lots of questions, but in this worksheet, just let me just try and find out. Here's another one. Same thing, reagents and conditions for. So there's an N triple bond N plus 1. So that means this thing over here was added. That's your reagent, right? Is that clear? NH2 turned into N triple bond N plus 1. That's NO2 plus HCl, and the temperature is less than 10. And the next one is alkaline conditions, NaOH aqueous, and you add this reagent. The N triple bond N plus 1 would go and attach itself to the benzene that is activated over here. Okay, so that's pretty much it. We'll try and finish organic, most of it, and then we'll do all the questions. Like, we'll do complete papers related to organic. Right now we're just picking a few questions, but we would be probably done by the next class. We'll probably be done by all of organic. Okay, let's continue tomorrow.
Sir, I have a question.
Haji.
Sir, how did you figure out the reagents and condition for reaction number 4?
The reagents is this is given over here. I told you that if you want to make an azo dye, it's got to be NaOH aqueous and the temperature's got to be less than 10. Right? Those are the conditions. And बाकी वो तो भी हम कर रहे थे ना कि if you've got N triple bond N plus 1, you have to decide okay, if you're making this dye, there are two things needed. You need a diazonium ion and you need an activated benzene to react with it. There's got to be two things, right? You need an N triple bond N plus 1 and you need an activated benzene to react with it. So if you look at the molecule over here, you would notice that this is the activated benzene that is reacting with it. Is that clear?
Yes, sir.
So that's where the reagent is coming in and the conditions are NaOH aqueous. Okay. So let's continue tomorrow then.
Okay, sir.
Lafez, take care.
Oh, sir.
Zeब, आवाज आ रही है?
Yeah.
हाँ, वो मैंने उसको देखना, वो मैंने ना शीट भेजी है.
Yeah, I just checked.
हाँ, उसमें देखना, उसमें शायद ऑर्डर में है. ठीक है?
Okay.
चलो ठीक है. ओके.
Thank you, sir. Love this.
Lafez.